Appendix 16 of Edison, His Life and Inventions. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Melissa. Edison, His Life and Inventions by Frank Lewis Dyer and Thomas Comerford Martin. Appendix 17. Edison's ore milling inventions. The wide range of Edison's activities in this department of the arts is well represented in the diversity of the numerous patents that have been issued to him from time to time. These patents are between 50 and 60 in number and include magnetic ore separators of 10 distinct types, also breaking, crushing, and grinding rolls, conveyors, dust-proof bearings, screens, dryers, mixers, bricking apparatus and machines, ovens, and processes of various kinds. A description of the many devices in each of these divisions would require more space than is available. Hence we shall confine ourselves to a few items of predominating importance, already referred to in the narrative, commencing with the fundamental magnetic ore separator, which was covered by United States Patent Number 228,329, issued June 1st, 1880. The illustration here presented is copied from the drawing forming part of this patent. A hopper, with adjustable feed, is supported several feet above a bin having a central partition. Almost midway between the hopper and the bin is placed an electromagnet, whose polar extension is so arranged as to be a little to one side of a stream of material falling from the hopper. Normally, a stream of finely divided ore falling from the hopper would fall into that portion of the bin lying to the left of the partition. If, however, the magnet is energized from a source of current, the magnetic particles in the falling stream are attracted by and move toward the magnet, which is so placed with relation to the falling material that the magnetic particles cannot be attracted entirely to the magnet before gravity has carried them past. Hence their trajectory is altered, and they fall on the right-hand side of the partition in the bin, while the non-magnetic portion of the stream continues in a straight line and falls on the other side, thus effecting a complete separation. This simple but effective principle was the one employed by Edison in his great concentrating plant already described. In practice, the numerous hoppers, magnets, and bins were many feet in length, and they were arranged in batteries of varied magnetic strength, in order that the intermingled mass of crushed rock and iron ore might be more thoroughly separated by being passed through magnetic fields of successively increasing degrees of attracting power. Altogether there are about 480 of these immense magnets in the plant, distributed in various buildings in batteries as above mentioned, the crushed rock containing the iron ore being delivered to them by conveyors, and the gangue and ore being taken away after separation by two other conveyors and delivered elsewhere. The magnetic separators at first used by Edison at this plant were of the same generality as the ones employed some years previously in the separation of seashore sand, but greatly enlarged and improved. The varied experiences gained in the concentration of vast quantities of ore led naturally to a greater development, and several new types and arrangements of magnetic separators were evolved and elaborated by him from first to last, during the progress of the work at the concentrating plant. The magnetic separation of iron from its ore being the foundation idea of the inventions now under discussion, a consideration of the separator has naturally taken precedence over those of collateral but inseparable interest. The ore-bearing rock, however, must first be ground to powder before it can be separated. Hence we will now begin at the root of this operation, and consider the giant rolls, which Edison devised for breaking huge masses of rock. In his application for United States Patent Number 672,616, issued April 23, 1901, applied for on July 16, 1897, he says, "The object of my invention is to produce a method for the breaking of rock which will be simple and effective, will not require the hand sledging or blasting of the rock down to pieces of moderate size, and will involve the consumption of a small amount of power." While this quotation refers to the method as simple, The patent under consideration covers one of the most bold and daring projects that Edison has ever evolved. He proposed to eliminate the slow and expensive method of breaking large boulders manually, and to substitute therefor momentum and kinetic energy applied through the medium of massive machinery, which, in a few seconds, would break into small pieces a rock as big as an ordinary upright cottage piano, and weighing as much as 6 tons. Engineers to whom Edison communicated his ideas were unanimous in declaring the thing an impossibility. It was like driving 2 express trains into each other at full speed, to crack a great rock placed between them; that no practical machinery could be built to stand the terrific impact and strains. Edison's convictions were strong, however, and he persisted. The experiments were of heroic size, physically and financially, but after a struggle of several years, and an expenditure of about $100,000, he realized the correctness and practicability of his plans in the success of the giant rolls, which were the outcome of his labors. The giant rolls consist of a pair of iron cylinders of massive size and weight, with removable wearing plates having irregular surfaces formed by projecting knobs. These rolls are mounted side by side in a very heavy frame, leaving a gap of about 14 inches between them, and are so belted up with the source of power that they run in opposite directions. The giant rolls described by Edison in the above named patent as having been built and operated by him had a combined weight of 167,000 pounds, including all moving parts, which of themselves weighed about 70 tons, each roll being 6 feet in diameter and 5 feet long. A top view of the rolls is shown in the sketch, one roll and one of its bearings being shown in section. In Figure 2 the rolls are illustrated diagrammatically, as a sketch of this nature, even if given with a definite scale, does not always carry an adequate idea of relative dimensions to a non-technical reader. We present in Figure 3 a perspective drawing of the giant rolls as installed in the concentrating plant. In practice a small amount of power is applied to run the giant rolls gradually up to a surface speed of several thousand feet a minute. When this high speed is attained, masses of rock weighing several tons in one or more pieces are dumped into a hopper, which guides them into the gap between the rapidly revolving rolls. The effect is to partially arrest the swift motion of the rolls instantaneously, and thereby develop and expend an enormous amount of kinetic energy, which, with pile driver effect, cracks the rocks and breaks them into pieces small enough to pass through the 14-inch gap. As the power is applied to the rolls through slipping friction clutches, the speed of the driving pulleys is not materially reduced. Hence the rolls may again be quickly speeded up to their highest velocity, while another load of rock is being hoisted in position to be dumped into the hopper. It will be obvious from the foregoing that if it were attempted to supply the great energy necessary for this operation by direct application of steam power, an engine of enormous horsepower would be required, and even then it is doubtful if one could be constructed of sufficient strength to withstand the terrific strains which would ensue. But the work is done by the great momentum and kinetic energy obtained by speeding up these tremendous masses of metal, and then suddenly opposing their progress, the engine being relieved of all strain through the medium of the slipping friction clutches. Thus the Cyclopean operation may be continuously conducted with an amount of power prodigiously inferior in proportion to the results accomplished. The sketch, Figure 4, showing a large boulder being dumped into the hopper, or roll pit, will serve to illustrate the method of feeding these great masses of rock to the rolls, and will also enable the reader to form an idea of the rapidity of the breaking operation, when it is stated that a boulder of the size represented would be reduced by the giant rolls to pieces a trifle larger than a man's head in a few seconds. After leaving the giant rolls, the broken rock passed on through other crushing rolls of somewhat similar construction. These also were invented by Edison, but antedated those previously described, being covered by patent number 567,187, issued September 8, 1896. These rolls were intended for the reducing of one-man-sized rocks to small pieces, which at the time of their original inception was about the standard size of similar machines. At the Edison concentrating plant the broken rock, after passing through these rolls, was further reduced in size by other rolls, and was then ready to be crushed to a fine powder through the medium of another remarkable machine devised by Edison to meet his ever recurring and well defined ideas of the utmost economy and efficiency. Note: Figures 3 and 4 are reproduced from similar sketches on page 84 and 85 of McClure's Magazine for November, 1897, by permission of S.S. McClure Company. The best fine grinding machines that it was then possible to obtain were so inefficient as to involve a loss of 82% of the power applied. The thought of such an enormous loss was unbearable, and he did not rest until he invented and put into use an entirely new grinding machine, which was called the three-high rolls. The device was covered by a patent issued to him on November 21st, 1899, number 637,327. It was a most noteworthy invention, for it brought into the art not only a greater efficiency of grinding than had ever been dreamed of before, but also a tremendous economy by the saving of power, for whereas the previous efficiency had been 18% and the loss 82%, Edison reversed these figures, and in his three-high rolls produced a working efficiency of 84%, thus reducing the loss of power by friction to 16%. A diagrammatic sketch of this remarkable machine is shown in Figure 5, which shows a front elevation of the casings, hopper, etc., removed, and also shows above the rolls the rope and pulleys, the supports for which are also removed, for the sake of clearness in the illustration. For the convenience of the reader, in referring to Figure 5, we will repeat the description of the three-high rolls, which is given on pages 487 and 488 of the preceding narrative. In the two end pieces of a heavy iron frame were set three rolls, or cylinders, one in the centre, another below, and the other above, all three being in a vertical line. These rolls were about 3 feet in diameter, made of cast iron, and had face plates of chilled iron. The lowest roll was set in a fixed bearing at the bottom of the frame, and therefore could only turn around on its axis. The middle and top rolls were free to move up or down from and toward the lower roll, and the shafts of the middle and upper rolls were set in a loose bearing, which could slip up and down in the iron frame. It will be apparent, therefore, that any material which passed in between the top and middle rolls, and the middle and bottom rolls, could be ground as fine as might be desired, depending entirely upon the amount of pressure applied to the loose rolls. In operation, the material passed first through the upper and middle rolls, then between the middle and lowest rolls. Footnote. The faces of these rolls were smooth, but as three-high rolls came into later use in Edison's Portland cement operations, the faces were corrugated so as to fit into each other, gear fashion, to provide for a greater rate of feed. Footnote. This pressure was applied in a most ingenious manner. On the ends of the shafts of the bottom and top rolls there were cylindrical sleeves or bearings, having 7 sheaves in which was run a half-inch endless wire rope. This rope was wound 7 times over the sheaves as above, and led upward and over a single groove sheave, which was operated by the piston of an air cylinder, and in this manner the pressure was applied to the rolls. It will be seen, therefore, that the system consisted in a single rope passed over sheaves, and so arranged that it could be varied in length, thus providing for elasticity in exerting pressure and regulating it as desired. The efficiency of this system was incomparably greater than that of any other known crusher or grinder, for while a pressure of 125,000 pounds could be exerted by these rolls, friction was almost entirely eliminated, because the upper and lower roll bearings turned with the rolls and revolved in the wire rope, which constituted the bearing proper. Several other important patents have been issued to Edison for crushing and grinding rolls, some of them being for elaborations and improvements of those above described, but all covering methods of greater economy and effectiveness in rock grinding. Edison's work on conveyors during the period of his ore concentrating labors was distinctly original, ingenious, and far in advance of the times. His conception of the concentrating problem was broad, and embraced an entire system, of which a principal item was the continuous transfer of enormous quantities of material from place to place at the lowest possible cost. As he contemplated the concentration of 6,000 tons daily, the expense of manual labor to move such an immense quantity of rock, sand, and ore would be absolutely prohibitive. Hence it became necessary to invent a system of conveyors that would be capable of transferring this mass of material from one place to another. And not only must these conveyors be capable of carrying the material, but they must also be devised so that they would automatically receive and discharge their respective loads at appointed places. Edison's ingenuity, engineering ability, and inventive skill were equal to the task, however, and were displayed in a system and variety of conveyors that in practice seemed to act with almost human discrimination. When fully installed throughout the plant, they automatically transferred daily a mass of material equal to about 100,000 cubic feet, from mill to mill, covering about a mile in the transit. Up and down, winding in and out, turning corners, delivering material from one to another, making a number of loops in the drying oven, filling up bins, and passing on to the next when they were full, these conveyors in automatic action seemingly played their part with human intelligence, which was in reality the reflection of the intelligence and ingenuity which had originally devised them and set them in motion. 6 of Edison's patents on conveyors include a variety of devices which have since come into broad general use for similar work, and have been the means of effecting great economies in numerous industries of widely varying kinds. Interesting as they are, however, we shall not attempt to describe them in detail, as the space required would be too great. They are specified in the list of patents following this appendix, and may be examined in detail by any interested student. In the same list will also be found a large number of Edison's patents on apparatus and methods of screening, drying, mixing, and briquetting, as well as for dust-proof bearings, and for various types and groupings of separators, all of which were called forth by the exigencies and magnitude of his great undertaking, and without which he could not possibly have attained the successful physical results that crowned his labors. Edison's persistence in reducing the cost of his operations is noteworthy in connection with his screening and drying inventions, in which the utmost advantage is taken of the law of gravitation. With its assistance, which cost nothing, these operations were performed perfectly. It was only necessary to deliver the material at the top of the chambers, and during its natural descent it was screened or dried as the case might be. All these inventions and devices, as well as those described in detail above, except magnetic separators and mixing and briquetting machines, are being used by him today in the manufacture of Portland cement, as that industry presents many of the identical problems which presented themselves in relation to the concentration of iron ore. End of Appendix 16. Recording by Melissa.